Welcome to IT Pro TV. I'm your host, Don.
Coming at you live from San Francisco, California.
You're watching IT Pro TV.
Hello, and thank you for choosing IT Pro TV, helping you learn wherever you go. I'm your host, Zach Memis, as we continue on with CompTIA Net Plus. And this is Routing Technologies Part 2. And Wes Bryant is here to once again help us through these waters. Wes, good to see you, sir.
Hey, how we doing? Hopefully, if it's murky waters, we can clear them up for you. That's right. So, we've been talking about routing technologies, right? And like Zach mentioned, this is a part 2. Remember, in the first part, we kind of set the stage for just some of the basics, right? The difference between an IGP and an EGP, interior gateway versus exterior gateway protocols, and we really talked about distance vector routing protocols, right? We were talking about RIP version 2. So as a real quick recap on that, just remember RIP version 2 is a distance vector routing protocol, and with distance vector protocols, keep in mind that it is the hop count that becomes the cost or the metric or what determines the best path.
Yeah, so you said there's two types of IGPs, distance vector and link state. Now, can you tell us more about that?
Absolutely. So with link state routing protocols, it's another type of essentially interior gateway protocol. And really the most common one that we use is what is known as OSPF. All right, that's Open Shortest Path First. And it's kind of interesting in the name. You can kind of see what's going on. It's the basis of routing, right? We want the best or the shortest path to get to a destination. Mm-hmm. Well, with Open Shortest Path First and link state routing, it's a little different in how we determine what the cost of a route is, right? The metric or the cost itself is going to be based on not just distance, and really it can be based on a lot of things, right? So where distance vector uses the destination and just distance, when it comes to link state, I want you to kind of change your mindset around it. I've been teaching this for almost a decade now, and one of the things that I tell students is that when you think of link state, change it around, and I want you to think of state of the link. If you think of state of the link routing, you can kind of figure out what a link state routing protocol is using to determine the best path, how it determines the cost, right? And that is through the state of the link, right? So it can use things like, for instance, it can use the bandwidth. What is the available bandwidth for it, if you will? What is the load utilization? What is the link reliability? Is it up? Is it down? Again, speed of the link, the bandwidth is one that is very, very important. And let me show you here. So unlike, remember, our distance vector protocol that's using hop counts, right, in the distance, when it comes to something like OSPF can say, hey, should I send this over, let's say maybe, let me finish my diagram there again. Should I send this over a 100 megabyte link or 100 megabit link? Should I send this over a 56K link? Should I send this over a 10 gig link, right? Well, you'll notice that 10 gig link is obviously going to be faster than a 100 meg link. So the 10 gig link has more bandwidth. It's going to could potentially be a better choice. So we look at the quality of the link, the speed of the link. Well, is that link up or is that link down? Again, so the reliability of the link. So, and administrators can actually set these. They set them through what are known as administrative distances, right? And you can manually let OSPF determine it, and there's a certain value or cost associated with different transmission speeds. But then administrators can override these if they want. If they want to manually define what the cost of a link is, they can, and they do that by setting what are known as administrative distances. And different characteristics of those links, as you'll go on to more advanced training, will learn that the administrative distances do differ in what the overall cost is. Now, kind of understand a little bit more about OSPF. OSPF is actually a pretty amazing link state protocol. It's the most common interior gateway protocol, much more so than RIP is today. And one of the reasons is that it doesn't have a hop count limitation. We don't have that limitation. It's very, very scalable. It has faster convergence times too. Now, Initially, it doesn't, all right? And let me tell you why. If we go back to our diagram here, OSPF, when these routers first come online, if they're using OSPF, then what they do is they actually broadcast their routing tables to all routers within the network. And you're probably thinking, maybe you're thinking out there like I am, well, wait a second, if RIP is only talking to the neighbors and broadcasting that communication, would that be more efficient than OSPF flooding that information out to every router on the network? And the answer is yes. At first, OSPF is going to saturate your network with a lot of communications, while all of these routers on this network try to converge. Again, convergence, remember that process of us all agreeing that we have the updated routing information. Now, here's where it starts to outperform RIP. At first, you get a lot of heavy traffic, as these routers are learning. Once they are converged, once they all agree, they have the updated topology information, if a link fails, unlike RIP, which continues to broadcast its routing tables, whether anything changes or not, OSPF does incremental routing messages. It says, I don't need to tell Zach about everything every 30 seconds. I'll just tell Zach, hey, guess what? That link's failed. Just that message goes, right? So you'll see that you get a faster convergence time because it's the incremental topology changes that are actually sent out across the network, right? Rather than having to inspect the whole routing table, figure out what we know, like RIP does, figure out if we know all of these routes, just to process the whole routing table to find one route that's changed. I'm just going to tell you what the change is. I don't need to give you the whole routing table, right? It also not only has faster convergent times, it has routing authentication, all right? Changes are propagated instantaneously. It doesn't wait, and we don't have to wait for it to get from neighbor to neighbor to neighbor to neighbor and wait until that converges really slowly, because the increment is just that incremental change, just that change is going to be propagated to all routers, if you will. It uses something known as the Dijkstra algorithm to recalculate topology changes, and it also uses things like, for instance, multicast updates. And the multicast communications, unlike the broadcast communication, remember, you got to be part of the group. A broadcast is one to everybody. A multicast communication that OSPF is using here is just one to the other devices that were within that group. So again, much more efficient utilization of your bandwidth. All right, let's see here. So that has our link state routing protocols. Again, remember that with your routing information protocol, it's an IGP, distance vector routing protocol, as well as OSPF that is using link state routing protocols.
Mm-hmm. So you mentioned link state protocols and distance vector protocols. So these are two separate protocols. Now, can there be a blending of the two?
It's interesting. Technically, we do have one that kind of sits, and this is a completely different topic altogether. We have one that kind of sits in between. Mm-hmm. It is an interior gateway protocol, and that's something known as EIGRP, the Enhanced Interior Gateway Routing Protocol. And you got to love the name. It's telling me what type of protocol it is, but it actually started out, it's a proprietary one, by the way. These other protocols are actually just open standards, if you will. Mm-hmm. With the EIGRP is actually proprietary to Cisco. It's a Cisco-based protocol. It was the successor to the earlier Interior Gateway Routing Protocol, also Cisco proprietary, IGRP. So you can consider Enhanced Interior Gateway Protocol as the upgraded IGRP. Originally, it was deployed as an Interior Gateway Protocol, but it can be used as an EGP, an Exterior Gateway Protocol, but more commonly an IGP. Now, Zach, you asked a question. A blending of the two. What do we have? Total protonic reversal, a crossing of the streams, right? That we said we should never do.
Getting back to the Ghostbusters thing again.
That's right. So what's going on here is that EIGRP can use distance vector technologies, but at the same time, it can also use, like our link state, bandwidth. What bandwidth is available? Is there, what's the delay? See, that's another thing that I didn't mention about link state. If there's a latency on the link too, so the quality of the link, the availability of the link, is it up or is it down, that's also in link state, but it's also in EIGRP, right? Because it's blending portions of distance vector and portions of the link state technologies, load utilization, again, link reliability, like we've said. better convergent times than the earlier IGRP, and it uses something known as dual, and that's the diffusing update algorithm. Not sure if that's going to be on the exam, but it is a characteristic of IGRP. So EIGRP, make sure I get that right. We don't want the old one, so that you'll know that on the exam. So that is one of those ones that kind of blends both characteristics of distance vector and link state to give you just a better routing protocol.
And I have another question. You mentioned the exterior protocols, right? The exterior. Can we talk a little bit more about that? Can you tell us a little bit more about that?
Definitely. So if we go back to the slide, remember one of the things that I told you, primarily we've got those 3 interior gateway protocols, right? We've got RIP, we've got RIP version 2, its successor. We've got, what else? OSPF, as well as IGRP, which is old by now, and then Enhanced Interior Gateway Protocol. All of these sit on the internal network. Well, remember, are internal to the autonomous system. Remember, they don't broadcast that information across autonomous systems. Well, there is one out there that is an exterior gateway protocol, and that's known as BGP. Now, BGP is interesting. In your, if you're following along with the exam objectives, one of the things that you'll notice is that they call it a hybrid. It's really technically a path vector protocol, and let me tell you, show you what I mean by that. All right. Remember that when I said the interior gateway protocols and the interior gateway routers, those are routers that actually sit on the inside of your network, and they sit there and they basically communicate their routing topologies inside of the autonomous system, but they don't let that information, broadcast that information to other autonomous systems, right? Now, this is where the border gateway routers come in, right? Remember, we have autonomous system numbers out there. It's an autonomous system, again, as a recap, is just it's a network that is under the control of a single administrative body and adheres to a single routing policy. Well, path vector protocol or border gateway protocol is what your ISPs use to communicate across the backbone of the internet in between these autonomous systems through the border gateway routers. These border gateway routers, if you will, they actually communicate amongst each other and share routing topologies, all right? And they do that with the border gateway protocol. It uses things like the path, right, through those autonomous system numbers, network policies, or rule sets to make its decisions to send communications basically along the backbone of the internet. This is how the core backbone routers, if you will, and this is how the autonomous systems communicate across the internet through BGP, or the border gateway protocol. All right, so we've come a long way here in our routing episode, or a couple of parts here now. We've talked about the routing protocols. We've talked about how, how they communicate. I do want to kind of mention something known as the route types, all right? When we talk about routing types, we've been talking about routing protocols. Routing protocols, these are dynamic protocols, and they allow us to generate what are known as dynamic routes. All right, dynamic routes means that if something changes, these routers, to the routes, if you will, something changes, a link goes down, there's a topology change, the routers can communicate and they can update on the fly. They can update the routing tables, removing bad routes, replacing and putting entries in there for destination networks with better routes, right? So that happens dynamically, all right? There's a benefit to that, and there's also another type of routing type that's called static routes too. Let me show you what I mean here. So I got a little diagram that we've used with our routers here, and a dynamic route is one that has been generated by these routers communicating, right? That analogy I used in the first part where Zach and I are talking, Zach says, hey, I got a better way for you to get to that destination in your car. I say, oh, okay, you know what? I want that destination. I'm going to use that path now, and I'm going to quit driving an hour to the same destination, right? That's dynamically happening, right? Well, there's also static routing, all right? And static routing is different in the fact that kind of like when we talk about DHCP, right, versus a manually entering an IP address. Remember, DHCP, the IP address can change potentially, and it's generated or it's given and leased over by a server versus me going in and typing and manually setting it. Well, that's what a static route is. A static route is one in which you're not using this routing protocol. No dynamic routing protocol is being used. In fact, the administrator is saying, hey, I want to define this route, and I don't want you to talk to anybody. I'm not talking to Zach. I've got the best route. I know the route. Zach's out of the picture. Sorry, Zach, picking on you there. But that's essentially what's going on. You're saying, I am going to tell you what route to use. I don't want you talking to these routers and trying to learn of a different route. Now you might say, well, wait a second, how is that beneficial? Well, it has its benefits. Understand that any time a router has to inspect a routing table or has to update routes and has to make these decisions, it's going to be using computational power, right? I mean, that's its decision. There's core logic in there, and it's going to use CPU, it's going to use RAM in order to make these decisions. Well, you can actually, if you know that there's only a single route in between two routers, you don't have, like in this case where we have routers that have multiple paths, well, there's no reason to process, a routing table. There's no, or I say process a routing table, there's no reason to try to make decisions, right? I can manually define that one route and we can get a potential for better performance because the router doesn't have to sit there and calculate algorithms to determine what the best path is. It looks at the routing table and says, I'm using this path. So you get that benefit, right? That speed, if you will. Now, the other thing too, for security purposes, if you're defining a static route and we're not using the dynamic routing tables, then it doesn't matter what all the other routers are telling you because it's not listening to that. It's going to use that static route. So even for security purposes, it's good because I don't communicate with anybody else to figure out how to get from this router to this router. I already know what the answer is, right? It's manually defined. Now that's the benefit, right? If you only got that one route, no reason to process a routing table, right? The bad part of this, the drawback is, and let me show you what would happen to dynamic routing protocols, is that if a link fails, what do the routers do? Now, whether you're using RIP or RIP version 2, which you're probably not going to, or you're using OSPF, even though there's a convergence times different, these guys could talk to each other and they could find out, oh yeah, that route's failed. All right, well, that route's failed, so let's get the traffic down another path. We'll remove that entry from our routing table, and we'll learn a better path, and we'll put it back in its place. Then if the route comes back up, well, guess what? We'll update that. That dynamically happens, right? That's why they call it dynamic routing. With a static route, if the route fails, you're still going to try to use it. The router isn't making a decision. The router isn't going to communicate. My path to my destination took me an hour and a half, and now I hit a bridge that was out. I don't have the ability and the luxury to call Zach and say, man, you've been out to this St. Augustine 100 times. I need a better path, right? I can't check Google Maps. I can't check the TomTom, if you will, and try to find a better path. I'm going to be sitting there waiting at the bridge. And that's the problem with static routes. It does have its benefit in the fact that if the route, you're not going to process a routing table, but if that route fails, unfortunately, you're still going to try to use it. And you're not going to talk to another router. So again, it does have its benefits, and like anything else, it does have its drawbacks. Now, there's another thing that we also need to be aware of too, all right? And the other thing is they talk about what's known as the default route. Well, inside of your operating systems, I can actually give you an example of this. You know, when we talk about a default route, what we're talking about is where do I send information if I don't know the destination network? Right? Well, inside of our computers, in fact, if we get back into our Windows machine here and we look again at our routing table, right? Notice that I have this 0.0.0.0. All right, well, what does that mean? Well, that means that we've looked at all the routes that we're aware of, and I don't have a destination. I'm looking at the destination network in this packet, this IP header, and I don't know where the network is. So where do I send it? Well, our computers send it to the default gateway, and they're doing that through what's known as the default route. This means if I search the routing table, I can't find the destination, I don't know where to send it, I'm going to send it to the default route here. And in this case, it's going to be my default gateway. All right, and you can see that our gateway is this right here. So it says anything that you don't know of, which typically your operating system can use ARP, the address resolution protocol, use its routing table, and it can send information on its local network, but it doesn't know how to send information on another network. So it says, oh, I don't know whose network this is, so let me go ahead, I'll look at my routing table and I'll send it to the all zero route, and that essentially is telling it to send it to the router. The router, it's up to its job to sit there and to determine where to send this information. So that is the default route, and I want you to be aware of it for the exam. Now, if you don't have a default gateway, you're not going to see the default route, all right? And let me kind of prove this to you here. I'm going to go ahead and open our Network and Sharing Center, and I'm going to completely change the properties of our network adapter, right? So I'm going to go to Internet Protocol version 2. We're going to go ahead and choose properties. And what I'm going to do is I'm just going to manually set an IP address. I won't be able to connect to the internet at all, but we'll go ahead and we'll just do 10.10.10. We'll do 255. Oops, there we go. Let's do 255.255.255. And I'm not going to set a, notice here, Zach, I'm not going to set a default gateway. We'll just leave that default gateway out of there. And we're going to go ahead and say, OK, close. You can see it's an unidentified network. It's not going to connect. But obviously, it's not going to be able to connect to the internet. Why? Well, let's see. Let's go ahead and we'll clear our screen here and we'll rerun our route print option. And I'll just do the V4. And notice that I don't have that. I've got the local network that I'm aware of, just like we did before. Right? I don't have the 172 here because remember, that's the network that this computer is now a part of based on its net mask. This is its IP address, and this is the broadcast address for that network. But notice what we're missing. Notice that the default route goes away.
It's not
right? And that's because I said, you know what? I don't want to have a default gateway. All right, so no default gateway, no default route. Now I'm going to go ahead and change this over to DHCP because the DHCP server is actually handing out a default gateway, which is what we want. And I'll go ahead and just obtain it automatically, change this over, and what it's going to do is go back to that DORA process, calling out to the network, getting an IP address, getting a subnet mask, and getting a default gateway. And if we clear the screen here again and we do a route dash print, oops, excuse me, we don't need a dash print, we need a -4. Notice that now that my default gateway is back, the default route is there. And again, it just says, if you look in this routing table and you don't know what that network is, send it to this route. And again, that will basically send it to your default gateway.
Perfect.
All right, so that has the majority of our concepts that we need to talk about. Now, I know we're getting a little close on time on this one, but I got 2 more topics that I want to mention, and they put that here in our routing section, and that is something known as network address translation and port address translation. Now, they call it NAT and PAT. All right, so what is NAT? All right, now, if you've checked out our IP addressing episodes, we talked about the fact that there are public IP addresses and there are private IP addresses. Remember, the public IP addresses are what we use to communicate across the internet. When I need internet access, what I do is I go to an ISP and I pay them a subscription or whatever the subscription fee is, and they essentially give you a public IP address. And that allows you to communicate with the internet. When you're not paying them, guess what? They revoke that public IP address, and now you can't communicate across the internet. Public IP addresses are how we route traffic across the internet. Unlike the private IP addresses, which I believe is RFC 1918, if you will, request for comment, 1918, these private IP addresses, they're just used internally on our networks. And ICANN, the Internet Corporation for Assigned Names and Numbers, and INA before that said, hey, we'll just set these to the side, and you can use them internally in your networks however you see fit. But you're not going to be able to communicate with the across the internet with them. So how is it that you can have 10 computers, let's say, on your internal networks? You get one IP address. I want you to think about your network right now, right? You probably got a cell phone connected to your Wi-Fi network. It gets an IP address. You probably got maybe a Roku. It's got an IP address. Guess what? It's communicating out there across the internet. Maybe you have an Apple TV as well. Maybe you've even got a television, right? A TV, a smart TV. It's connected to the internet. All these computers are communicating across the internet. Yet when you went to your ISP, you were only given a single public IP address, all right? That's through network address translation. And what it is it's a packet mangling. It's a packet manipulation. It's a manipulation of the IP header. And let me show you what I mean by this, all right? So you are leased a public IP address, let's say from your ISP, all right? You have one public IP address. Now, on your internal networks, your machines are using private IP addresses. In fact, we can kind of see this here. If I run my IP config, we can see that this DHCP server is actually configured to give us a Class B private IP address. You can see 172.16 and then .anything. That's in that Class B private IP range. But let me see if I can. I can ping a public IP address, and sure enough, I'm getting communication. So how is it that I tell you that you can't communicate across the internet with a private IP address, but yet I can just ping a public IP address. So it sounds like I'm lying to you, right? Not really. What's going on here is that in this instance, what's happening is the network address translation device is receiving that packet, right, with that IP header that has the private IP address in it. And what it does is it says, okay, I'm going to go ahead and I'm going to remove that private IP address, and I'll bookmark it in my table so I know which computer it came from. And I'm going to go ahead and put my public IP address on it and send it out across the internet. All right, now when it comes back into the network, what it does is it takes that public IP address off and removes it. Oops. It removes it. That's why you shouldn't manipulate a slide on the fly here. And it removes it and it replaces it with the private IP address. I'm going to get this right eventually here. So what we have essentially is a translation, right? We get the ability to manipulate the packet. Now, you also have what's known as port address translation, and port address translation is the fact that it also will check the ports, right? It will, like for instance, in your home networks, right? What it also will do is it'll say, hey, I'm going to do the same thing here, but in order to keep track of the communication, I'm going to actually pay attention to the port number as well when I put that in that database. And when that information comes back, essentially what we're going to do is it's going to inspect the port, and then what it does is it will replace the internal private IP address with a port and deliver it to the endpoint. All right, so you got port address translation and you got network address translation. Again, network address translation and port address translation, they're kind of both using NAT, but one is actually inspecting the port, that layer 5 port address, if you will. Or TCP/IP port. Now, the last thing I want to mention too is something known as port forwarding. All right, and again, this kind of comes back to like port address translation, but you have your devices that can pay attention to the ports that are associated with a communication. Well, when you receive a communication inbound into a network, if you're doing port forwarding, you can say, you know what, the device, let's say the router, I want you. Anything that comes in on port 3389, when you see that traffic coming from the outside in, and I can see that that TCP/IP port is port 3389, I want you to take that communication and forward it to this one computer. It's called port forwarding, right? Port forwarding is a way that we can take a certain type of traffic based on its port number and send it to a specific computer inside of our internal network. That's port forwarding. So know what port forwarding is as well. Again, like I said, as you go on to more advanced training, you're going to see a little bit more on how to configure port forwarding as well.
Now, once you said that we would learn a little bit more about advanced configuration and advanced courses, right?
Yeah.
So can you tell us a bit more about that, or can you give us a glimpse?
Yeah, I can give you, absolutely. You know, so when we talk about just basic port forwarding, right, we can actually show you here. So I'm on a Linksys router. If we take a look at my computer here, you'll see that we're just in the basic web interface. And one of the things that you'll find this a lot in your applications in gaming, because gamers will expect a certain traffic. Yeah, here's another way that you might see this, right? And you might see that when you're doing things like online gaming and stuff, that they're expecting a certain amount of certain port values and certain types of traffic to be sent to a certain computer. If I've got 5 computers within my internal network and only one of them is my gaming rig, then I want to make sure that all of that gaming traffic goes straight to that computer and doesn't go to any other computers, right? So what we can do is we can do port forwarding here, and you usually on your home routers and stuff like that, you'll find it under application and gaming. I just happen to be in Linksys, right? And what we can do is we can say, hey, I want to forward a specific type of traffic. Let's say, for instance, it doesn't have to be, I'm just giving gaming as an example, but notice it's saying, if you see a port for 53, in this case it's DNS traffic, I want you to send that to, let's say, a computer on my network, and let's say it's 192.168.1.12, all right? Then what I can do is I can enable that, and we can go ahead and save those settings. And when we continue, let's see if it does save it. Yep. Then what it's telling me is that, hey, anytime I see DNS traffic bound for port 53 in this case, it is going to see that, inspect that information, and it's going to send it to this one computer. Right, so this just happens to be an example of, doing a single port forward for a single type of communication. And again, it's going to identify that. You've seen it there for a second, that it was going to identify it based on its port number. So notice it's saying external port coming in. I see the traffic. In this case, now we've changed it to HTTP traffic. When I see this traffic come in, send it to this computer or this IP address, right? So
Great.
Basic port forwarding there. Like I said, it can get more advanced, but at least you can kind of see like the basics and what is going on behind the scenes.
Fantastic job as usual, Wes. And Routing Technologies Part 2, an essential episode in the CompTIA Net Plus series. Make sure you watch all of them, and you're in the course library anyway. There's hundreds of other videos there, all designed to help you go further. And tell everybody you know about IT Pro TV. They'll be very glad you did. I'm Zach Memis.
And I'm Wes Bryan.
Thanks for watching. We'll see you soon.
Thank you for watching IT Pro TV.